The Wrath of God, and how Wolfgang Pauli brought order to the quantum revolution. What if the universe exists because nature refuses to let two things be exactly the same? By the time Wolfgang Pauli entered the story of quantum mechanics, physics was already in turmoil. Max Planck had shattered classical physics by proposing that energy comes in tiny packets. Albert Einstein made the crisis even deeper by arguing that light itself behaved like particles. Niels Bohr then constructed a remarkable model of the atom in which electrons occupied fixed energy levels, but no one really understood why those levels existed. Next came Louis de Broglie, who dared to ask one of the strangest questions in the history of science. If light can sometimes behave like a particle, could particles behave like waves? His answer transformed quantum theory and inspired Erwin Schrödinger to develop his famous wave equation. Werner Heisenberg went even further, abandoning visual pictures altogether and building a theory based only on what could actually be observed. One breakthrough followed another, but there was still a problem, a very big problem. If electrons naturally seek the lowest possible energy, why don't they all simply collapse into the same state? Why doesn't every atom become a tiny featureless ball with every electron piled into the lowest orbit? The equations had become increasingly sophisticated, but this question remained unanswered. Then Wolfgang Pauli supplied the rule that made the entire quantum world possible. Pauli was one of the most brilliant and intimidating physicists of the 20th century. His colleagues respected him so deeply that many were terrified to present new ideas in front of him. He became famous for his devastating criticism. One remark, whether or not he always used it in exactly these words, became legendary. This isn't right. It isn't even wrong. They say, to Pauli, a bad scientific idea wasn't merely mistaken. If it couldn't even be tested or logically evaluated, it wasn't science at all. His sharp intellect earned him another almost mythical reputation. Experimental physicists joked that laboratory equipment mysteriously broke whenever Pauli entered the room. They called this the Pauli effect, and countless stories circulated about instruments exploding, electrical systems failing, or experiments collapsing simply because Pauli happened to visit. Whether coincidence or superstition, the stories reflected something very real. People believed Pauli possessed an almost supernatural ability to expose flaws. Among friends, he became known as the Wrath of God. The nickname fit perfectly, because what Pauli brought to quantum mechanics was judgment. Imagine entering a theater where every seat in the front row offers the best possible view. Classical physics predicts that everyone would rush to those seats. Nature does something entirely different. Every electron wants the lowest energy state, yet somehow they refuse to pile on top of one another. Instead, they spread out into different arrangements. Pauli realized this wasn't an accident, it was a law. His exclusion principle, proposed in 1925, states that no two electrons can occupy exactly the same quantum state at the same time. That phrase, quantum state, sounds technical, but the underlying idea is surprisingly intuitive. Think of every electron as having a complete identity card: its energy, its orbital, its angular momentum, its spin. If every item on two identity cards is identical, nature simply rejects the arrangement. There is no negotiation. The second electron must occupy a different state. That single rule explains something extraordinary. Atoms don't remain organized because electrons politely cooperate. They remain organized because the laws of nature refuse to let them become identical. Suddenly, Bohr's model made much more sense. Bohr had correctly proposed that electrons occupy discrete shells around the nucleus, but his model didn't explain why those shells filled in such a regular pattern. Pauli supplied the missing reason. Electrons aren't merely choosing different energy levels. They're forced into them. As each available quantum state becomes occupied, every additional electron must move into a new one. The atom builds itself, one forbidden duplication at a time. One final puzzle remained. If two electrons cannot occupy the same state, why do two electrons fit into the same orbital? The answer came from another remarkable quantum discovery. Electrons possess a property called spin. Despite the name, they are not literally spinning like tiny planets. Spin is a uniquely quantum property with no true classical equivalent. You can think of it as one additional piece of an electron's identity. Two electrons may occupy the same orbital because their spins differ. One has one orientation, the other has the opposite, and their identity cards are no longer identical. Nature is satisfied. This single principle explains far more than atomic structure. It explains chemistry itself. Hydrogen behaves differently from helium. Carbon forms four bonds, oxygen forms two. The repeating patterns in the periodic table are not arbitrary. They emerge naturally because electrons fill quantum states, according to Pauli's exclusion principle. Without it, there would be no familiar periodic table, no complex atoms, no stable molecules, no chemistry, no metals, no rocks, no biology, quite literally, no solid matter. Everything you can touch owes its existence in part to Wolfgang Pauli's simple but profound rule. Seen from the perspective of our quantum on the treadmill journey, Pauli occupies a unique place. Each scientist before him answered a different question. Planck explained how energy is exchanged. Einstein revealed the particle nature of light. Bohr explained why atoms don't immediately collapse. De Broglie suggested matter itself behaves like waves. Schrödinger described those waves mathematically. Heisenberg forced physicists to abandon classical certainty altogether. Then Pauli asked a different question. What prevents the quantum world from collapsing into complete disorder? His answer transformed quantum mechanics from a collection of remarkable ideas into the architecture of matter itself. Pauli's career hardly ended there. He introduced mathematical tools that became central to quantum theory, helped establish the importance of symmetry in modern physics, and proposed the existence of the neutrino to preserve one of physics' most cherished conservation laws. In 1945, he received the Nobel Prize in Physics for the exclusion principle. Yet, perhaps his greatest legacy was his relentless insistence that ideas survive rigorous scrutiny. He was the physicist everyone wanted on their side and few wanted as an opponent. Because when Pauli found a flaw, he usually wasn't just criticizing. He was protecting physics from fooling itself. That may be why the wrath of God was ultimately a compliment. Every revolution needs visionaries who imagine impossible things, but every revolution also needs someone willing to say, no, that can't be right, Tate. Quantum mechanics had plenty of dreamers. Wolfgang Pauli made sure the dream held together.